Thank you. So I might be walking around, and hopefully if I'm closer to the screen, the laser pointer will give me something. I doubt it. So I'm Martin Gillar. I'm from Waters Corporation. I've been analyzing oligonucleotides for 30 years. And today we're going to talk about longer oligonucleotides with the aspect of sgRNA and maybe tRNA are coming as a new therapeutic modalities. In this little cartoon, you can see the antisense oligonucleotides, 20-25 mer. What was considered to be challenge 25 years ago is now routine. We have LC-MS methods, we have a separation, we have a capillary electrophoresis. Now new challenges is coming in the form of new modalities, these longer oligonucleotides. So pushing it up to 100 nucleotides long, the resolution, it is actually quite difficult, but good news for those of you, I may ask the audience, who is doing the sgRNA analysis currently? Hands up. Yes, we have a lot of people. Good news for you, the existing LC-MS methods are actually adequate. It's stretch, but they are adequate to the task. I have a bad news for the people who do mRNA analysis. We are not there yet. Method development for these very long RNAs, it's still ongoing. So, as I said, the solutions are very efficient UPLC or UHPLC. LC-MS methods are well developed, and I will show you some methods how to convert these long oligonucleotides into shorter oligonucleotides and make the task easier. So, as I am first speaker, I thought it's gonna be wonderful. I can talk in basic terms about chromatography, about separations, and then I thought I will introduce these methods, and then I realized that it may not be as simple as I hoped, because I'm an analytical scientist, I know LC-MS, I have done chromatography for ages. The audience may not even know some of my abbreviations. So, briefly, ion pair reverse phase chromatography. It's basically a reverse phase chromatography. I hope you know what I'm talking about, where we include in the mobile phase some ion pairing agents. And they increase and improve the separation and the resolution of oligonucleotides by length. Hillick method, I hope that you know it's a hydrophilic interaction chromatography. Why do I know about these two techniques, or why do I speak about those two techniques? First, because those two are LC-MS compatible. Typically, when I talk about resolution, I say resolution of ion pair reverse phase chromatography, let's say up to 100 mers long. Resolution of Hillick is less. Maybe after 30-35 mers, this resolution plateaus and you cannot go much further. I also hope that you know that this sample, these numbers, these mysterious numbers, 15 to 35 mer, those are the numbers of nucleotides in the sample. This is a standard mixture. We make it, I design it at Waters. We now use it for almost everything. For example, when you run in a problem and you think your column is bad, you inject a standard. If the peaks are where they should be and you have a resolution, all is good. The error is in you. So, LC-MS compatibility. About 5 years ago, maybe 7 years ago, Hillick method came into vogue because people, presumably LC-MS people, hate ion pairing agents, and they want to do ion pairing agents free chromatography, and that would be Hillick. And they claim this would be more amenable for LC-MS. As you can see, those check marks, the green, both of methods are LC-MS compatible, but both methods I also score orange check mark because all of them have their own specific difficulties, and we'll get to it. So Hillick is not necessarily better than ion pair reverse phase. There are other two methods that 5 years ago, although size exclusion chromatography, SEC, has been known for ages, and it is a super useful method for biomolecules. It's a method that separates small molecules from medium, from large. That would be perfect, but hardly anybody has tried it for oligonucleotides. There is very little in literature. Recently I did some work, so we have good data. This is one of the examples. So for your information, size exclusion chromatography is a low resolution technique. Yeah, we can resolve maybe 20 peaks or so, even with these modern columns they have a super high resolution. But to my surprise, I was able to resolve, let's say, oligonucleotides up to 15 mer by single nucleotide. And further on, we can resolve even more. The caveat is it's done in buffers, so it is not LCMS compatible method. Ion exchange is classical method for separation of anionic compounds, like oligonucleotides, and it is a good method to resolve oligonucleotides, let's say up to 100 nucleotides long. If you go beyond that, even some mRNA, you will have to use more than half molar salts to elute these nucleic acid species, and that is definitely not LCMS compatible. Also, it's a harsh on your instrument and so on. So that is why some people don't like that method. Although, as I said, it's still classic. So we are today talking about long oligonucleotides up to 100 mers. And here is my example of what ion pair reverse phase chromatography can do. This is a standard oligo T ladder. I mixed roughly equimolarly those pairs. So you can see that short oligonucleotides, wonderful separation. Longer ones, you have to push it. So I used long column, sub 2 micron particles, shallow gradient, and I can go maybe to 69, 70. The resolution is good. You can see that 68 mer, it's still nicely resolved. And we have some resolution even for 100 mer, but I guarantee that if you're looking at n-1 in a real life scenario where it is 5 to 10%, the resolution is not going to be that, what you see here. So, I also may point out that I put their chromatographic definition of resolution. Typically, when we say in chromatography, we have a resolution of 1. That's the RS1. Above those peaks, 69, 70 mer. We say this is a wonderful resolution, but this may not be true for scenarios where you have a massive peak and on a tail of it or in front of it there is a small peak. The resolution is not going to be that great. So we understand that. LCMS people. Do I see hands? Who is the LCMS person here? Do you intend to use LCMS for these analyses? Do you want to move it into your lab? There is a few people. So when Mark invited me to contribute to the workshop, I thought that we have to talk about basic terms about mass spectrometry of oligonucleotides. So you have a peak. If you go with LCMS compatible mobile phase into mass spec, you get the spectrum, the electrospray spectrum on the upper left corner. And what do you see? Like in peptides, like in proteins, and unlike for small molecules, where you say, when you see one peak as a mass, for the larger molecules, you get multiply charged states. It is a probability that if you have a 20 mer oligonucleotide, there might be 1 or 2 dominant charged states, and not much beyond it. If we go to 30 mers, there will be more charged states. In my case, 8 and 7 are the dominant charged states, but your signal spreads among many peaks. If I would show you here and you can see it in literature, mass spectrum of 100 mer, you would see 50 charge states there, right there. And none of them is particularly dominant. It's like a Gaussian envelope. So your signal splits. That's one of the tricky part. The other part is, if you look at the -3 peaks, the red mass spectrum detail, what you see is that main peak. Beyond it, there is a sodiated version of it, and then there is a potassium, and there is a 2 sodium attacks. This is still considered to be high-quality MS spectrum. You have to control your sodium, potassium, alkali ions mostly, very well. Otherwise, you may end up with a massive adaptation, and your peak that you have there, -3, may not be the dominant, maybe even invisible. So you have to control your mobile phase purity. This is not a problem for something like antisense oligonucleotides, 20 MERS, a little adaptation. 30 MERS, more. 100 MERS, you can imagine that you've got problem there. So that's one thing. And finally, let's talk about what happens here. For those of you who are not mass spectrometrists, you see multiple peaks there, right? Those are isotopes. There is a C13 in addition to C12. There is oxygen 18 and so on. So, as you have a very large molecular weight, you don't get one single nice dominant monoisotopic peak. You actually can end up in a situation like with 100 MERS, where you don't even see where the monoisotopic peak is, because it is low abundance. So let's talk, and why am I talking about it? Let's talk about the resolution. So in mass spectrometry, we have a resolution that is defined as a mass of your peak divided by peak width of that ion. So if you are measuring ion of 1,000 Daltons, you can, and your peak width is 1 Dalton wide, your resolution is by definition 1,000. For your information, most of the nominal resolution quadruples, single quad, even triple quads, they still have the same resolution, about 2,000 plus minus. If you apply this mass spectrometer to analysis of antisense 25 MER oligonucleotide, I simulated here for -4 charge state. What do you see? No isotopic resolution. You have to have a resolution of, let's say, 20,000. It's some kind of routine TOF analysis. And now you see the isotopes are now resolved. If we go to 100,000 resolution, you may start to get the isotopic resolution for even these 100 MERS. Why am I talking about it? Why is it important? It is important because let's say that you have your antisense oligonucleotide, you know its mass, you can analyze it. You can do this analysis without isotopic resolution. But if you don't have isotopic resolution, you remember there are many charge states. If you don't have isotopic resolution, you don't know what the charge state it is, and you may be in trouble to getting what the mass is. Unless you know up front, you may be in trouble. So we rely on this. Typically, if we have isotopic resolution, if, in this case, the delta mass in between all of those isotopes is 0.25, quarter of Dalton. If I know it's quarter of Dalton, by definition, this is a 4 minus charge state, and I can do the little math, and I can get accurate mass. If I want to have a monoisotopic mass for that particular peak, that's the monoisotopic peak, I can easily calculate it. However, I already alluded to it, if you have something like 100 MER, this is the isotopic envelope. Where is my monoisotopic peak? It's so small that I may misassign it, and if I misassign it, I just made a mass error by 1 Dalton. So, to make the long story short, if you are doing some analysis of unknown impurities, you don't know what the mass is, you need isotopic resolution. And even if you have the isotopic resolution for very long oligonucleotides like 100 MERS, you still could occasionally make an error. If you're doing some MSMS sequencing where you're generating a lot of fragments, you will need isotopic resolution. At least, let's say 20,000, but better to have a higher resolution. So we get over it, and I'm back in my more familiar path to chromatography. This is a paper that we published recently in 2023, and this is a comparison of what you can do with ion pair reverse phase and HELIC for these full phosphorothioate. We have phosphorothioates, and this what we call full length product, FLP. That's the black peak. On the left panel, you can see that so far I was showing you these beautiful equally spaced chromatograms of oligo-DT ladders. This is a real life. The spacing between the peaks is not that regular in the real life because the sequence matter. So in this case, we are showing what we already knew and experienced for a long time, that if you have a -1 peak, and that's truncated by T or A, you actually can resolve that peak beautifully. It's right here. But if you're unlucky and your N-1 is truncated by C or G, well, that's much tougher resolution. Sequence matter. What was quite interesting for the HELIC was that in HELIC it's reversed. It's the different case. C and Gs, because those are the hydrophilic oligonucleotides, they resolve better in this case, and you have more difficulties to deal with -T or -A. I could talk more about this, including that oxidized products, the so-called PO impurities, I hope you know what it is. In ion pair reverse phase, they elute prior to the main peak. This is actually quite fine separation. Unfortunately, usually it is obscured with your other peaks that are eluting there. For HELIC situation, we intriguingly have these impurities eluting afterwards, so they can be better resolved from N-1s and so on. So, because HELIC is new, it's relatively new, in oligonucleotide world, I thought that I will just remind you some methods for method development. So if you do, this is presumably LC-MS compatible conditions, but you still do need to have some buffers. We typically use amide premier columns up to micron particles. It works beautifully. This is again my sample, 15 to 35 mer oligo-T peaks. And if I do pH 8, all looks good. pH 6, pH 5, you start to get peak tailing. So my first advice, stay close to neutral or slightly basic. Why there is a tailing, I'm not going to talk about it, but non-specific adsorption to the column hardware is messy. You can lose some oligonucleotides in your sample due to non-specific adsorption. Second thing, people who propose the HELIC to be LC-MS compatible, the sensitivity really depends on the concentration of the buffer. The less of the buffer you have, the better you are. Unfortunately, if I go to low concentration, let's say 10 millimolar, I start to have slightly distorted peaks. If I go below, especially below 5, my peak starts to get really tailing and distorted. So again, my second advice is stay close to maybe 20 if you have to go to 10 millimolar ammonium buffer, ammonium acetate buffers, neutral pHs, pH 8, you will be good. So, size exclusion. Size exclusion has not been used widely for oligonucleotides, but I guarantee it will be, because it is quite intriguing. In this case, this is the recent paper. This is a poly-A tail analysis. This explains why I chose these poly-A standards in the length of 15 to 150 mer. This is the range where we analyze the so-called poly-A tail in mRNA world. So I needed to know if I can resolve these oligonucleotides by length, And it apparently works the best for this size exclusion column that has a 250 angstrom size. That's the right pore size to resolve these oligonucleotides. The smaller pore size is actually fantastic for short oligonucleotides. The 450 angstrom is not so good for short, but it starts to resolve these hundreds mer long RNA, so that would be applicable to mRNA fragmentation analysis or something. Even better, we have a 100 angstrom pore size column that's a brand new, and that might be even more applicable to mRNA analysis. Just for your information, if somebody was quick enough to notice this purple chromatogram, this is my synthetic oligo-RA, ribonucleic acid standard, and all of these, this tail, those are N-X failed sequences. So you can use this method for quick and dirty quality control check of your synthetic oligonucleotide synthesis. Finally, I am at my favorite method, which is ion pair reverse phase chromatography. I have presented this slide before. And I always make the point to say that this is optimization of ion pairing systems. Of course, there are amines, triethylamine, dibutylamine, hexylamine. What do you choose? This is confusing, right? What do you choose as your ion pairing agent? So we made in this paper from 2022, there is a lot of data underneath in this paper, and we used one column, this is 50 millimeter long column. We used the same gradient of acetonitrile and same temperature, and everything was constant for all those experiments except of the choice of mobile phase. If we choose just a pure ammonium acetate, which is by definition not an ion pairing agent, this is a pure reverse phase mode, what you see, the separation of my 15 to 60 mer peaks is not there, and this is weakly retained. And no matter what you do with your gradient and how you define the method, you will not get the separation. So when we include diethylamine, triethylamine, butylamine, the longer oligonucleotide, or the longer the ion pairing agent alkyl chain is, the more hydrophobic it is. So the oligonucleotides become more retained and also better resolved. It's a simple trend. And so if you also notice these numbers underneath of 20 mer peak, this is a number percent of acetonitrile that I need to elute my oligonucleotides. So basically, you have to use so much of acetonitrile for these more hydrophobic alkyl amines that you are converting that separation more or less to charge-charge interactions, like in ion exchange. And the other interaction that is present here, the hydrophobic interactions, is less prevalent. That may be important for something that you do, and I may talk about it later. And finally, LCMS compatibility. There are plenty of papers published that discuss different ion pairing agents and different counter ions and so on. In my hands, I basically arrived to a conclusion that if we use alkyl ammonium solutions buffered with acetate, 100 millimolar ammonium ion pairing systems, we get no signal MS. If we go to 25 millimolar, we get miserable signal. Reducing it further to 10 and 5, we finally get some decent signal. This is a logarithmic scale for a signal of 20 mer peak. And because it's a log scale, the difference between this and this scenario is like 5-fold improvements. So yes, it does work better, but if I, instead of with these buffers, and by the way, I cannot go much below this concentration because then my ion pairing is so miserable that I lose all chromatographic separation. So we cannot go much below. The alternative is Instead of acetic acid, we use this hexafluoroisopropanol, which is a fluorinated alcohol, but because it's perfluorinated, it behaves like a weak acid. In solution, it's an acid. You can use it to buffer your base, alkyl amines, and make these wonderful buffers. Here I show 5 millimolar and 10 millimolar buffers of different alkyl amines. And it pretty much doesn't matter which one I use. In all cases, I get 2 to 3 orders of magnitude better mass spec signal, 100-fold compared to acetate. Conclusion here, alkyl amines don't matter all that much, but the acetic acid or formic acid, if you want to use that one, is really the thing that kills electrospray signal. And even though there are some alternatives to this HFIP, hexafluoroisopropanol, there are some other perfluorinated alcohols. So far, I haven't seen anything that works better than HFIP. I know that there was a session in this morning. People were talking about stereochemistry. So let's talk about it briefly too. If we have a phosphorothioates, it's a slightly different beast because here we designed an experiment and we played with all these different buffers. This is another paper from 2022. We have 5 peaks. The first one doesn't have any isomers because it's phosphorodioester. And then we have a 1 ps or 2 ps linkages up to 6 ps, and this is the number of isomers there. 2 isomers up to 64 isomers. They are resolved chromatographically. And because they are chromatographically resolved, they widen and broaden your peaks. So if we use the upper chromatogram, just ammonium acetate, pure reverse phase. Peak number 1, no resolution. Peak number 2 have 2 peaks. Oligonucleotide number 3 resolve into multiple peaks, etc. Hence, your choice of alkyl amine is important. If we choose more hydrophobic ones, triethylamine, this chromatogram, already has some of these separations suppressed. The peak number 5, this one has, it looks like a peak, even though it has a 64 partially resolved diastereomers. If we take it beyond that and we use dibutyl or maybe even hexylamine, we use, again, so much of organic, so much of acetonitrile to elute these peaks from column that the hydrophobicity of reverse phase is suppressed, and because the hydrophobicity is the thing that affects the stereo resolution of those isomers, we compress those isomers into one peak. It's not perfect. The first peak, peak number 1, is always narrower than the peak number 5. It's like 2x wider. But you could do the separation of phosphorothioates. The other tool that you have in your disposal is temperature. You could use high and low temperature. In here we show this peak number 5, 64 diastereomers. And if I do 20 degrees C, I am partially resolving them into many peaks. Not all of them, 64 peaks there. But if I dial it up to 90 degrees C, I collapse successfully this diaster resolution. So high temperature and more hydrophobic alkyl amines, your ion-bearing systems, would be the solution for fully phosphorothioated analysis. In sgRNA, we often, as well as for some modern siRNAs and so on, we use only terminal positions that are phosphorothioated. Maybe 2, and if we protect both ends, it's like 2 and 2 at each side. We could actually be interested in separation of all of these. So this is an siRNA. The blue peak is full phosphorodiester, only one peak. if we phosphorothioate one linkage, this one PS, that's the red chromatogram. We have two isomers resolved. If we do instead thioation of 3' end with two positions, now we can resolve 4 isomers in certain conditions. The better conditions for this kind of separation is more reverse phase-like, weak alkylamines and diluted ones. So in this case, we use just 15 millimolar triethylammonium acetate. And we have a resolution. If we want to suppress it, we use higher concentration or stronger alkylamines. All this resolution is lost. So if you wish to perform this stereo separation, I think you can do well even with 100 MERs like sgRNAs. So this is an example of 100 MER. What did we learn about the separation? We could use efficient column, a relatively long column, 100 millimeter long, packed with 2.5 micron particles, and this is a 4.6 millimeter ID column. 1 nanomole injection, I see this is a crude synthesis. So I see if I do diligent counting, there is about 95 peaks that you can count, plus few more is hiding on the front of this peak. So this resolution is actually quite good. Can I take it into purification? Scaling it up, this is a classical how the purification works. If you overload the column, you get a higher signal, peaks get a little bit fat, they also shift a little bit. Like this peak eluting here shifts from 22 minutes to maybe 20. And if you load even more, it will shift more. For example, this group also shifts, this group also shifts. It's like a bulldozer is pushing in front of it all those early peaks. But good to know that this peak is here, is here, is here. You don't necessarily lose the resolution. So when I do these type of lab scale purifications, I'm not greedy, I start collecting from a peak top, and somewhere in half height, I stop my collection. If I do it like that, I'm getting 95 plus purity, even for these 100 MER oligonucleotides. Remember what I told you about the sequence contribution? If your N-1 is a C or G, well, you will see more of it than if it is A or T. So you could do these purifications. Very little has been said in literature. We have some papers that mentioned it about method development. So let's talk about it. If you choose your alkylamine, in this case is octyl ammonium acetate, 25 millimolar, that fixes your selectivity. There's very little you can do. If you change your gradient slope, it's not going to change your selectivity. If you change your initial organic condition strength, it's not going to change your selectivity. It's pretty much fixed. So the only thing that remains to be done here is if you are separating something like 35 MERs, you could do 1% organic per minute. If you need to go to 60 MERs, you do 0.5% per minute. If you go to 100 MERs, you could do 0.25% of acetonitrile per minute. That leads into very shallow gradients and very long separation times. Who is patient? Not me. So your optimization here could be that once you've selected your gradient slope for your separation, you can then adjust this entire train of peaks and their elution time by selecting your initial gradient strength. So this is shown here. Here we do 1% per minute, 1% per minute acetonitrile. Starts from 36% of acetonitrile. If I want to achieve shorter separation without a loss of resolution, I just start from 45.6 and the entire train of peaks shifts. You don't lose the resolution. You can see these numbers are pretty much the same. Arguably, yes, the early eluting peaks are now squished like an accordion. But that's not what you are after, right? You are analyzing and purifying your late eluting peaks. So finally, we have a method. Let's talk about LCMS of these long oligonucleotides. I have an example for 30, 40, 50, and 80 mer RNA. I'm using here my 10 millimolar with 100 millimolar dipropylamine with HFIP. It's like one of my trusted choices for oligonucleotides. And I see a bunch of peaks. Those are, by the way, high quality syntheses that I get. Those are purified oligonucleotides. And yet, even after purification, you can see that there are a lot of other impurities. We can see them. So separation-wise, I'm quite happy. LCMS, I can get mass for all of these peaks, even up to 100 mer. The main peak will give you wonderful MS information, and you will get accurate mass from it. Now the trouble starts if you wish to do MSMS sequence confirmation. We routinely, pretty much any LCMS vendor, we are performing routine MSMS analysis sequencing, confirmatory sequencing, I must add. We know upfront what the sequence is. So when we do the confirmatory sequencing, it's routine for 20 mer. It's okay for 25 mer. It's get tough for 30 mer, especially if somewhere in the sequence you have the 2-O-methyl or 2' fluorinated modifications. Those are the positions that fragment very inefficiently. You may have a gap in the sequence there. So getting beyond that length of 30 mer into 100 mers, I don't think I can do it now. Definitely not routinely. So what are my options? A lot has been published recently about RNA mapping, especially in the context of mRNA. And mRNA is 1,000, if not thousands, of nucleotides. If you deploy some of the specific RNases, it will chop this long molecule into relatively short, very manageable oligonucleotides, but it will produce a lot of them. So it's messy. And I will talk about it on Friday if you want to see messy chromatograms. But in case of something like 80, 100 mers, this is a marriage in heaven. You can beautifully clip this 100 mer into 10, 20 oligonucleotides. Each of them are quite neatly resolved here. And each of them you can detect their mass. And if you want to, which we do, you can get routine sequence analysis of these 5 to 10 mers, 15 mers. You do want to have a software for it, I remind you. If you don't have a software that takes care of all the data interpretation, that is very tedious work. Luckily, we have confirm sequence, which will look at all of these oligonucleotides, assign all these fragments, and give you the spectrum. Here I focus on this 8 mer peak. I focus on the smaller signal. Yes, they're all within 5 or 10 ppm accuracy. This is what you choose in your method. And it's all very believable. My mass spectrometric colleagues, when they click on all these ions and investigate the raw data, they say, I do believe the assignment. So in conclusion, we have various methods for analysis of oligonucleotides. I am still partial to ion pair reverse phase chromatography because it is, in my hand, the most flexible and most efficient. What you can do with method development we described, you choose your gradient slope, you choose your initial conditions, that's it. Besides that, you better choose highly efficient columns, sub 2 micron particles or something like that. If you choose 5 micron column, your resolution is never gonna be satisfactory. Hydrophobicity matters, we know it. Phosphorothioates, they complicate your work, but you could choose either conditions to promote their resolution of the diastereomers or suppress it, depends on what you want. And we have LCMS, HFIP is still the king, and you could use acetate maybe up to, let's say, 5 millimolar, because I assume that you are not doing any clinical studies in LCMS of teeny tiny femtomoles. You have enough of sample to play with somewhat lower sensitivity of acetate buffers if you want to. And of course, if you are doing these sequence confirmations, you better have a software. Waters has software, other vendors have software for MSMS analysis as well. So with that, I'll be happy to answer your questions if you have any.
Thank you, Martin. Any question?
I have a general question, maybe I missed it. So, as you mentioned, the alkyl acetates, they are not suitable for LCMS at higher concentrations. How, if I look at a certain alkylamine and I look at the separation efficiency that can be achieved with the ion pairing reagent, if I just look at the alkylamine buffered with HFIP versus the same alkylamine buffered with acetate. So there has to be an advantage, obviously, with the acetate. Can you comment on this or how strong this effect is?
This is a very good question. I completely glossed over it. If you have some of the alkyl amines and they are very hydrophilic and you use them in buffer that is comprising of HFIP, they suddenly start to behave like much stronger alkyl amines, and even stupid triethylamine behaves to give you quite good results. Some of the data and explanations have been proposed in literature. That paper from 2022, I believe, showed also a nice explanation why that happens. And there is more work coming. Basically, if you use just a plain acetate versus HFIP, is exactly as you said. HFIP has gives you some other benefits for the separation.
Okay, thank you very much.
One more question, because we are running already a bit late. And then you guys can talk to Martin after as well.
Very nice work, Martin. You mentioned that you were able to separate one incorporation of phosphorothioate, and the separation of RPSP was very clean. Were you able to compare that with chirally pure compound and assign the peak, that where does RP stand and where does SP stand? And is it reproducible if you change, let's say, the basis? So my question here is that, do you have a profile which you can now use as a fingerprint using your method to show that the RP comes first and SP comes next?
Yes. So this all has been worked out. 1985, Wojciech Stats and others,
right,
they did these dinucleotides. Later on, we also played with stereoselective exonucleases and endonucleases, some preferring R and some S forms. And it is, as you say, the early eluting are the Rs. And if you have RRR form for like former, it elutes first, and SSS form elutes latest. So you can elucidate the retention, but it is partially sequence dependent, both resolution as well as retention. And it has not been worked out to my satisfaction and probably to your satisfaction. So there is still more work to be done.
Right, but it's a nice method to further explore in that area.
Mm-hmm.
And since I have the microphone, I was going to ask you one question. So you show an example on the purification. So the question is, you show that reverse phase is, or ion pairing is possible for the purification. Now, are those stationary phases available in bulk? So you could pack your own column?
You could ask for the bulk. You will pay with your arm and leg, I can assure you. But you could go to 3.5 micron or 5 micron particles in prep. That is all good, 30, 40 mers, all works well. If you want to do very long oligonucleotides, you will have to slow down the separation, the flow rates and everything. And you can then get the resolution, but at the expense and massive expense of time. Rather than doing it in 20 minutes, you would be doing it in 2 hours.
We have time.
Yep.
Overnight. Okay, thank you, Martin, for excellent presentation, and you will be here all week, so you